iC House. Integrated Circuits.
So, hello and welcome to our webinar about boosting the performance of angular position sensors. I will introduce you to the new iC-NQE sine-cosine signal converter. My name is Joachim Quastorf and I'm responsible for the sales and applications engineering of encoder-related circuits, especially interpolation ICs, and that brings me also in touch with a few input sensor devices. Our focus of today is on position sensing, and I will try to explain what you as an applications engineer need to know about signal processing. I will give you an overview of typical angle sensors, along with a historical view on IC design to explain where we are going. This is of course related to the increased requirements and demands for precision that has led us to the iC-NQE design. Beyond theory, in a second part, I will look at some hardware to give you a live example on commissioning a sensor and to show how easy it can be to achieve an excellent measurement accuracy. And of course, we will have time for your question at the end. Now for the beginning, let me introduce you to the application with a closer look inside the sensor's electronics. In this sketch, from the left to right, we got the position sensor, then a channel, which is actually just the cable, and on the right side, the PLC, which may ask you for a specific interface protocol. Now, since the typical motion sensor must provide information about speed and direction, and maybe certainly also position, at least for a north marker, it's clear that the single processor in the sensor's core must process more than just a single input signal. It does not matter if the sensors are optical, magnetic, or inductive. In most cases, we have a combination of an incremental scale, here under level 1, plus an absolute scale here under level 2, and both sections may employ multiple detectors. However, for the connection, if you want to stay analog, you can do so. The chip I'm going to explain provides the necessary cable drivers. And certainly, for the digital output, the chip also offers the most typical interface of encoders, such as the AB quadrature, the SSI or BiSS interface. So what are the challenges you are facing in your sensor design? Well, certainly you have to deal with assembly tolerances, environmental conditions such as dust, oil, maybe humidity, and also electromagnetic interference immunity could be of concern. Now it's up to you to select a sensor suitable for those environmental conditions. Regarding the electronics, the chip has to deal with level changes introduced by changes in air gap and also over temperature. Same applies for offset drift. I don't know any sensor without any drift. And maybe distortion, and finally noise. This is something the electronics have to cater for, especially by stabilization, maybe of the sensors energizing, or then by an automatic gain control. The offset drift could be compensated supply dependent or also by a dynamic correction. For distortion, we can counteract by a linearization feature. For noise, there is a good idea to add some digital filtering. Now, for the factory calibration at side of the manufacturer, you will ask for some reasonable efforts. In our case, as showing it today, we mount a reference encoder below, so this speeds up your linearization. But on site, when finally the customer needs to do the calibration, it's nice to have a standard interface such as a BiSS interface and also the well-known 1 volt peak sine-cosine analog interface. Now this is what the iC-NQE does cover completely. Let me show you what kind of sensor technologies are available to generate the position signal. I'm starting at the bottom here. Hall encoders are widely used in on-axis, or you may say end-of-shaft applications, such as small BLDC motors, or HMI input devices. The Hall sensor is relatively immune against interference or stray fields, but it only offers you one input cycle. That's not very much. A higher resolution is usually achieved if you go off axis. That is when the IC or sensor does not look at the axis centrally anymore. Typical examples here are a pole wheel encoder or a tape encoder using XMR sensors. Now, regarding optical sensors, there are various reflective and transmissive detectors available that generate a significantly higher input resolution. So in this case, you can get a higher input resolution than with any magnetic type of detector. Now, what I'm going to point out is here that the input frequency climbs up with the input resolution, but not so distortion. So we have to expect the highest nonlinearity when the input resolution is poor. So the question is, what is the amount of distortion we have to deal with? Well, going back a few decades, you had to deal with a few percent in harmonic distortion, especially when connecting an AMR angle sensor. Nowadays, however, signals are much cleaner, which means that the signal processor must work more precisely and offers a much smaller step size during calibration. So this has changed IC design a lot. We followed the trend towards higher precision, and certainly in parallel, advanced CMOS technologies enabled a higher complexity. Roughly speaking, we are dealing now with 10 times the number of transistor functions than 2 decades ago when you compare the iC-NQE series and the new NQE. Let me get back to the application and ask what could be on your wish list. This sketch divides the sensor converter into 3 segments: input section, processing core, and output section. Now the inputs must be able to handle low-level signals as well as high-level signals, maybe almost rail-to-rail, so that you can provide a full-scale signal for the converter core. Besides, the input section is in charge of outbalancing all the primary signal errors so that we can output well-conditioned sine cosine signals on the cable. The index inputs are in charge of handling an index signal. That can be done by a simple comparator, or besides, you can have an absolute data interface to pass on initialization data. For the core, you may ask for high resolution, accuracy, and speed. Well, throughput requires bandwidth, and that increases noise. So that was a point that challenged our designers to optimize their approach. And finally, they decided to combine the fast vector tracking conversion with digital filtering. For the outputs, that's the section where you don't like to waste any board space. So to solve the space constraints of small read heads, we have therefore integrated all the line drivers required to go directly on the cable. Your choice of a converter device may also depend on the type of error correction you need. You can imagine each IC needs to be cost effective, so any design comes with trade-offs. And it's hard to say that one device fits all. Now, depending on the type of error correction, systems may or may not provide accurate angle data immediately after power up. While a dynamic error correction requires input cycles to settle in, meaning a scale in motion, the static correction can provide a higher angular accuracy directly from standstill. This is true at least when you restart at the same temperature as at the time of calibration. If you are dealing with local scale errors, you need to understand that a dynamic correction reacts afterwards, and therefore can only compensate for previous disturbances proportionally. To correct a local disturbance, a lookup table would be nice and required, which corrects the position data to the point. Let me give you an overview of contemporary converter designs. Flash converters use comparators that work in parallel and can therefore be quite fast. This concept is usually limited in resolution because chip space is costly. The sample and hold converters are used with absolute encoders, mainly optical encoders, which provide much higher input resolution and much higher input frequencies, of course. There is a conversion time, and quadrature outputs are typically missing, so this kind of converter is not so famous for magnetic systems. Delta Sigma ADC-based interpolators, such as the ICT-W29, feature a fully digital error correction. That eases commissioning the sensor, but the angle is calculated and latency introduced. But keep in mind, this time is still 10 times faster than conventional resolver converters used for servo motor controls. The new iC-NQE prefers a vector tracking principle, an approach for real-time conversion at nearly no latency. We added two features: a position filter to fight edge jitter, and a feature what we call iCal, which allows us to compensate signal distortion individually for each input cycle. Let's closer look at the iC-NQE. What are the news? Well, the device runs off 3.3 and 5 volt at a reasonable power consumption. The resolution is higher, we reach 16 bits. Accuracy has been improved, allowing an INL down to 0.02 degrees per input cycle, of course. And the device is faster, so that linear applications can benefit from higher travel speeds. But let me jump on the output interfaces here on the right. We included cable drivers for a differential 1 volt peak sine-cosine signal, cable drivers for RS-42, allowing you to output RS-ABZ or alternatively UVW, an embedded transceiver for BiSS, so this is directly the receiver and differential transmitter for the cable. Alternatively, or not using this interface, you can go on a 4-pin SPI for embedded applications. And we completed the I2C interface here now for system internal communications. And optionally, I mentioned it, the 0 inputs can be altered to run an absolute data interface, a clock-driven SSI interface. With regard to performance benefits, I would like to distinguish between analog and digital. Now, on the analog side, we have a zoom-in programmable amplifier which can handle low-level and high-level signals. The signal condition accuracy for offset, phase, and ratio allows you to calibrate down to a 40-bit angular accuracy. XMR sensor drift compensation is done by a supply-dependent offset correction. Sensitivity compensation can be done by an automatic gain control. So this allows you to run the device anytime at full scale for best signal-to-noise performance. Besides, we improve the cycle tracking, allowing now high-frequency inputs up to 500 kHz, so you don't lose the tracking. And the analog output can be used for signal inspection and monitoring purposes. On the digital side, we have the full auto-calibration for easy commissioning. You can enable dynamic signal error correction, so this compensates, or this allows a lifetime drift compensation. For the compensation of distortion, that's a static correction, we can do it with 1 kilobyte of data, so that we can compensate the nonlinearity over up to 256 input cycles individually per input cycle. Then we added the noise filtering, can be switched off or switched on, and in certain levels, so this fights edge jitter. Besides, on the digital engine, there's a 32-bit period counting, allowing you a very long travel distance to recognize input cycles, and of course we have a lot of status bits for operation monitoring. Well, the device is going to come in 2 packages, a 20-pin TSSOP and a 32-pin QFN. For the TSOP, we are pin compatible to the existing iC-NQ series, the iC-NQE and iC-NQC. In a direct comparison, we have a much higher precision times 8 and can allow a higher input speed times 2 at least. Resolution is higher, so this allows to output up to 2,500 AB cycles or binary numbers. Index gating input is accompanied by an alternative, the absolute data interface. ABZ outputs generate up to 10 megahertz, what means an edge rate down to 25 nanoseconds. You can have UBW with up to 32 cycles per revolution. The temperature sensor is embedded, allowing to monitor that the device operates in a safe condition. An alarm output can lit up a LED if you like to see if the input signal is gone. I2C allows you to access the external EPROM and other I2C devices, and that is the preferred interface to connect an embedded MCU if there's any. The BiSS interface is profile compatible. It allows you small CSCs and longer CSCs, things which are quite typical. Now, when we have more pins, that allowed us to include the sine-cosine line driver for the cable, the same for the ABZ output drivers. We have 3 stages of RS-42 outputs, differential. The BiSS interface transceiver, alternative is the 4-pin SPI, and some more pins. The PWM output is there, and also a reset input, allowing you to trigger a low power standby. I'm now coming to application examples. I'm starting with an optical encoder, the reflective ICPR1456, which reads a small code disk of just 14 millimeters with 256 lines. While due to the small optical radius, it's quite clear that the sensor initially generates offset and also a phase error. But don't worry, the auto-calibration of the iC-NQE can easily engage for an auto-calibration, what finally improves our interpolation accuracy. Well, these screenshots are hard to read, but trust me, that way we improve the interpolation accuracy by a factor of 4. Well, single condition is not everything. So if you mount the sensor, you have to deal with a disk runout and maybe height wobbling. And as visible on this small INL screenshot here, there's also an optical crosstalk from the index visible. Now, all those measurements I'm presenting in the following have been taken from the iC-NQE GUI as a screenshot. And the data comes from a device chain. There's our device on the test plus a reference encoder in chain, so the data is evaluated by the NQE GUI. So this is a typical INL reading for this reflective sensor. Well, employing iC-linearization, you can really get it down to impressive values. Let's talk on magnetics. In this example, I'm using an AMR sensor, in this time an IC-SM2 2mm AMR sensor to read a pole wheel of 80 millimeters in diameter. Now what you get as an input signal is a long wave error due to a eccentricity, and also a magnetization disturbance comes visible, most likely caused by a local scratch. Again, using iCar, this can be linearized at least to a certain point. That is quite good for this type of sensor. Now, I'm repeating this. Now it's not a radial target, it's now an axial target, but I use the same sensor SM2. And initially, I get a larger eccentricity error. That is due to the fact that this is much smaller in diameter. And I did not yet calibrate here offset, so that's quite typical. You see each of the poles. iC-linearization on the right side also compensates this. Now let's go on axis. TMR is the more challenging. If you install a precision magnet and send a TMR sensor to the axis, you get a nice input linearity like this one here. So this is already a good result. But again, using iCal, you can reduce it to very excellent values. Now inductive, I'm passing it over. We will see it live, but let me explain it how it is working. We have a PCB-based coil providing some energy, and then there is a rotor, a metal target, which introduces a field disturbance. And this field disturbance is sensed by receiver coils. So finally, you get amplitude modulated high-frequency signals, and that needs a demodulation IC. And in our demo, I'm using the GI-22 as a front-end chip. That's a setup, actually. So on the left-hand side, the GI-22 is passing on its analog signals to the iC-NQE. What I did not yet mention, there is also a second track here, since we need an index signal. You see this small block inside here. So this front end already digitizes my 1 CPR input signal, which is absolute, so that the iC-NQE can source an absolute initialization angle here over its ADI interface. Okay, the setup we are going to see is using a drive with a reference encoder. So this is in a BiSS chain, passed on the device under test, queued up to the GUI so that we can do the INL reading. The sensor is driven by the drive, of course, and the analog signals are connected to the NQE and then over the sine cosine output linked to the Lissajous analyzer. Here I'm using a synthesizer 2, which is a nice tool for encoder inspection. Besides, we have ABZ outputs linked on a picoscope so that we can look at the jitter. Okay, now let me switch over to the demonstration. As explained, so that's our drive with the reference encoder. Here we have the sensor PCB, the inductive sensor. The evaluation is on this PCB, passing on the signals to the synthesizer and besides on to the BiSS adapter. That's the new one, MB8. You can also use the MB5U. Now, initially, when we look at the Lissajous figure, we can see that there's the input signal, the orange one, and the output signal, the blue one. Our target signal, the 1 volt peak signal, is the white target circle. Now, if I change my air gap, so this changes my input signal, and we can easily see also the output signal is following that change. So, well, now we're going over this 1 volt signal, and that was too much. Now, I need to enable the automatic gain control to get it compensated. Doing it here. Takes a while, but we can see that now the device controls the sine cosine output to exactly to this 1 volt peak signal, and input signal is still very strong. Now, when you like to get a noise-free input signal, you may like to operate the inductive sensor at a distance where it has not been designed for. In this case, you allow higher input distortion. Well, it's not fully visible here. Let me switch the scaling here. Now, that's a typical input distortion for this type of sensor if you go to close. But now, having this calibration feature, I can easily compensate this. So finally, we end up. Oh yeah, I missed to activate something. What's going on? So now it comes back. Maybe I was too close, so the input signals has overdriven my converter. Try it again. Okay. Sorry, I did it a little bit too tough to the target. So finally, I'm ending up with 0.01 degrees in accuracy. That's an excellent precision for this kind of sensor. Finally, let us look at the quadrature outputs. So what we see here is our 2048 CPR and from 8 CPR input. And if I calculate now the jitter, we are around 6 to 7%, what is quite good reading here for for this type of setup. Okay, this finishes my presentation here. Let me switch back to the slides. So, as a summary, the iC-NQE offers you diff-free precision inputs, a fixed or adaptive gain. You can have this outstanding single condition accuracy, optionally a dynamic gain control with offset drift compensation. The vector tracking interpolation ensures an ultra-low latency, and afterwards you can correct the distortion per input period. The digital noise filtering allows you an outstanding AB jitter. Period tracking is up to 500 kHz implemented, high moving speeds. We have output stages RS32 and the BiSS transceiver, conditioned sine-cosine output, and run of 3 or 5 volt over the full temperature range. For embedded application, we have SPI and I2C, allowing you to access I2C devices and also additional user memory. So overall, this solution is space-saving, cost-effective due to the extended grade of integration. And the GUI-supported self-calibration eases your commissioning. And finally, again, it's a drop-in upgrade of existing iC-NQE applications when you go for the 20-pin TSOP. We are going to have an evaluation board, so it looks like this one. It has a lot of connectors on there and also BiSS input, BiSS output connectors, allowing you to set up a measurement as I did here. So that is under preparation. We aim at mid of June to have it available. Now I'm finally done and ready for your questions. Thank you.
Thank you, Joachim. Excellent presentation. So we have a few questions that we'll answer, and just for the people listening in, we will run over a few minutes, but this will be recorded, so you will get to see the Q&A session as well when you get the video link afterwards. So let's get started, Joachim. How are the values for the iCal function collected, automatically or manually?
It's done by the GUI software.
Okay, good. Next question. There's actually two questions. Does iC-NQE support also 11 microamp or only 1 VPP? Sine cosine?
No,
for example, Heidenhain.
It's high impedance input. There's no current to voltage conversion.
Okay. And second question here. What is the maximum interpolation factor and how does it affect the latency?
It has nothing to do with latency. The maximum factor is 16 bits, allowing you in a factor times 4096, I think 65,000 something per input cycle, of course. In this demonstration, I'm resolving 19 bits, 3 from the input sensor and 16 bits on top.
Okay, excellent. There's another question here. Is a reference design PCB plus BOM plus layout available for developers?
You can look at the PCB layout we did on the iC-NQE evaluation board.
Okay, good. And the last question here, what is the expected unit price? I guess 1K or 10K?
Yeah, we are close to 6 euro.
6 euro.
It depends a little bit on the package. The QFN is a little bit high in price due to the extended features.
Okay. Next question. What is the... Oh, it's very fast. What is maximum signal frequency for AGC and iCal?
iCal does not limit it. ABC allows up to 10 MHz output.
Okay. Is a reference encoder mandatory for calibration here?
For the time being, it is, since the GUI does not yet support a time-dependent calibration, but we are working on it, so it's just a question of a few weeks.
Okay, excellent. Is the encoder link interface supported, such as present on the TW28 or
no, it's
not?
Sorry.
It's not. Okay, good. Let me see here. What is the main functionality difference between TW29 and NQE?
TW29 uses a linear delta sigma ADC and then does everything in a calculation. So this is subject to latency. Here we are passing on conditioned analog signals to a nonlinear tangents converter. So it's totally different. So this is a tracking converter, which is directly behind the input angle. There's less than 1 microsecond in latency. Before the filter can, if you introduce acceleration, the filter will also introduce some latency. At constant speed, it does not.
Okay, next question.
Position lag, I meant position lag. Sorry.
Okay, no worries. Does iC-NQE have gain offset phase adaptation during operation?
It does. We did not yet disclose it. I'm very sorry. I demonstrated it partly here. It's not yet visible on the datasheet.
Okay. Compared to the TW3, has the dynamic response been improved? For example, in case of impurities?
That is something I did not evaluate yet. So a nice test to set up. I didn't do it up to now.
Okay. Does it fit to third-party encoder redhead that gives some sine cosine feedback? What is the spec of the signal?
I think it does. So we can also directly connect 1 volt peak signals from standard encoders. Yeah.
Okay. Is the NQE suitable for functions for safety applications?
Well, the chip design has not been done under safety ideas. Of course, everything what we know, what functions we need to allow a seal-approved device has been included. Also a CRC, and you can cross-check the memory, the configuration during operation. But it is not a seal-rated device up to now, since this would require the complete chain of input sensor and PLC. So that's not what we did so far.
Okay. What about the function at the 3.3 volt supply and 1 VPP with typical level of 2.5 volt?
No problem at all. We scale down the input signals, so can run it at 3.3 volt.
Okay. And now we're going to take the last question. Is there a version of this one for linear encoders?
No, it's the same device. So we have 32 bits in period counting, and if there's one index, you can exactly say at what input period you do some compensation. The problem is that when you go linear, you have many more input cycles. What is going beyond this 256 pointer to our lookup table, but you could still compensate all input cycles equally, not individually, but all trading it as it would be the same input. So this can be done. So if there's distortion present which repeats, you can improve the accuracy here.
Okay, excellent response. Thank you. So this concludes our Q&A session. We're sorry that we ran over for 5 minutes, but I hope you enjoyed this very good presentation from Joachim. And last but not least, just want to let you know that we will be at Automatica in Munich from the 24th to 27th of June, and you will find myself, Joachim, and our other colleagues here. So we look forward to see you there, and talk to you very soon, and thank you from the podium. Bye-bye.
Bye-bye.
iC House. Integrated circuits.